Hey everyone, so today we're going to start chapter 7 in Steck on operational amplifiers. So for those of you in the course, that means we're skipping chapter 5 and 6. Chapter 5 is on field effects transistor, which are actually more useful transistors and they're actually easier to make. But fundamentally they work the same way as the BJT, the bipolar junction transistor. And then chapter 6 is actually on vacuum tubes, which are very useful if we're dealing with, well, if you are dealing with certain types of sensors. For example, the ones we use in particle physics are called photomultiplier tube, which are essentially just vacuum tubes. And how they operate is actually very useful for folks in that field to learn, but it may not be for everyone. So I'm going to skip over that too, especially since we won't have labs on it. So we're going to go over operational amplifier in this chapter. Okay, and these are called op amps, and these are going to be our first integrated circuit. Integrated means on a single chip, you actually have multiple components inside it, and it's designed so that you just connect the chip to something, and it has some properties that you can customize depending on how you make that circuit inside the chip. So basically, you can think about an integrated circuit as a little breadboard that's been shrunk to fit in a tiny chip, and then and the ones we're going to use are these LF411s. So it looks like a little spider with 8 legs on it, and I'm going to get to play around with those in the lab. Inside this LF411, since we're introducing your first integrated circuit, there's actually 1 transistor, 2 transistor, 3, 4, 5 other transistor with some resistors in between them, and a couple of diodes, because we want a couple of diode drops, a little capacitor, and you may start seeing, especially this left-hand side here, right? Even though these are going to be PNP transistor as opposed to NPN, you may recognize, oh, this looks kind of familiar, right, to this diagram on the right here, right? So because essentially this entire left side of the op amp is a differential amplifier, okay? So remember that differential amplifier amplifies differences between the 2 inputs, okay? And this particular case, you have one application on this end, and the output on one side, on this Q2 side, actually goes to the Q4 and Q5 also. So you have a second stage of the application. That's the word I didn't think of at first. Okay, so it's actually a dual stage transistor amplifier, differential transistor amplifier. So basically this Q1, Q2 amplifies the signal once, and then it gets amplified again. And I don't know the beta of each of these individual transistors, but if you combine these together, you get a gain of about 25,000 on the LF411. Okay, and I always say about because remember that these are based on these beta functions of the transistor, which you should not depend on, but you just know that, oh, it's just going to be some big numbers you multiply by. Okay. You may wonder what this Q3 is for. Q3 is actually just a extra input impedance, so that when you go from this, well, if you look at the differential amplifier from last module before, right, the input impedance is basically going to be dominated by this REE, so this is essentially the same resistor there, and instead of just going through one set of transistor, it goes through a second, so you just get an extra factor of REE. So so the input impedance is also amplified a lot in this case. Okay, as I stated, right, the gain of this LF411, since it goes through 2 stages, it's actually about 25,000. This is the book, not just this book, everyone denotes this as A, And this A is known as the open loop gain. We're going to see why this is called open loop gain, because it's basically the gain of this operational amplifier if you don't put anything in the output. Okay, so it's like an open circuit on the other side. Okay, that means, right, if you put in, the difference between the two inputs here, right, it's only 1 millivolt, right? 1 millivolt you can barely see on your scope, by the way. You're going to get 25 volts, which is, bigger than our power supply provides. Okay. You only get this 25 volt, of course, if you have a plus or minus 25 volt power supply. Okay. Since we're going to be running these at about plus or minus 15 volts, what happens is that if you do have a 1 millivolt difference between your two inputs, it's going to get amplified until it gets to this point where your power supply cannot provide the voltage needed in order to keep increasing the output. So it's going to get railed at 15 volts. So this is a very similar concept to when you were studying these transistor amplifier, the effect of the amplifier clipping, right? It's pretty similar to that. Okay. And once again, these beta value changes with temperature. So you could get 25,000, you could get 5,000, you could get 100,000. 25,000 is just like the nominal values. Okay. Okay. And in this case, right, it seems like we built a extremely powerful differential amplifier, but there's no way for us to actually use that power because A, that application is not reliable, B, it over amplifies even tiny changes in your voltages. Okay, this is why we never use these operational amplifier in this open loop mode, but this is just a way to specify things so that you have an open loop gain of 25,000, and that's how you specify these things, but you never actually use it like that. Okay, so what we're going to do is we're going to use these operation amplifiers in closed loop mode. Okay, closed loop mode. In closed loop modes, the op amp will follow these two golden rules. Okay, the rule is that the input draws no current. Okay, and this is because the input has this very large input impedance, right? Remember this beta squared times REE. RE is going to be like a 50K resistor already. You multiply that by beta twice, right? You're going to get something on the order of like a gigaohm. Okay, so it draws almost no current. But as you know, in order for something to measure anything, right, just like your multimeter, it draws a little bit of current in order to figure that out, right? So you cannot actually have an input without that doesn't draw absolute zero current, but it draws a little bit, and we're going to see what that specification is for the LF411. The second rule is that the op amp will change the output, right, so that basically Vin plus and Vin minus, remember these has two inputs, okay, and the cool thing is that the book specified this like this. In some other textbook, they may just say V plus and V minus, and sometimes that gets confused with the VCC and VEE, so don't, so it's actually nice that the book specify Vn plus, Vn minus, okay, and remember this gets amplified by this open loop gain, okay. What the op amp is going to do when you have this closed loop mode is going to try to make that to be zero. Okay, it's going to try to make the two input the same. Okay, that's sort of the way you should think about this. Okay. Okay. And of course, this is up to the point where you have enough VCC and VVE, the positive and negative voltage supply, so that the output does not get railed. Okay. So let's do an example and see how we analyze something that behaves like this. Okay, the first one is going to be the simplest one. It has no component. It just has the the op amp itself. And what you do is you connect the input to the positive input, the Vin plus, and then you just connect the negative input to the output. Okay, like wait, what? How will this behave? Okay, all right. So following golden rule, let's see, number 2, right? We're just going to use rule number 2 here. It's going to try to make Vin plus equal to Vin minus, okay? While Vin plus, right, it's just Vin. Okay, so make sure to note that these are different, could potentially be different, In this case, it's the same, right? But they could be potentially different if you have like a resistor or something like that. Okay, right? That's that equal sign. Okay, actually, I'm not going to write vertical equal sign. Let's just make it horizontal. Okay. Well, Vin minus is connected to the output, so this is actually V out also, right? So by this relations of, you know, these 4 steps of relationship, right? Yeah, Vn is actually going to be equal to V out. So therefore, if you're solving for V out over Vn, which tells you the gain of whatever thing you're dealing with, right? That's going to be equal to 1, right? Because these two are equal to each other. All right. Okay. So, you know, not a very interesting amplifier, but one of the things that we noted last time with transistor is that gives it changes the input impedance of something you're attaching to, right? So if you needed something to increase your input impedance, just pop an op amp in front of it, and then you increase the input impedance by basically a factor of 1 million. Okay, well, 1 million to 1 billion. Okay, so let's move on to something a little bit more interesting. This is the inverting amplifier. Okay, so hopefully the name will tell you what it kind of does already. Right, it's an inverting amplifier. So in this case, we added R1 to the input and then R2 to this loop here between the output and the input. This is known as the feedback loop. Okay. Okay. This is the input loop. Okay. Okay. Technically, the input, you know, are both the V in plus V in minus, but since we're only attaching things to the V in minus, then that's the R1's only on that is the only thing in the input loop. Okay. First of all, we're gonna apply rule number 1 first. Rule number 1 tells us that the inputs draws no current. If I can spell that. No current. Okay, that means if I define, I'm going to erase a little bit here, let's put the labeling, right? If I define this to be I, right, this current will flow through R1, the same current will be on the other side, right, because I haven't deviated yet, okay? Current cannot flow this way into the input, right, because that's following rule number 1. Therefore, the current has to go up here through the feedback loop through R2 and get to the output. Okay, so that's applying rule number 1. There's only one current. Okay, okay. But rule number 2, oops, right, states that, okay, V in plus is going to be equal to V in minus. Okay, within the operating range of the op amp. Okay, all right, so what does that tell us? Okay, since this V in plus here, V in plus, V in minus, right, is tied to ground, right, V in plus is going to be tied to ground. We're going to set that to be 0. That means V in minus is also tied to ground, right? But it's not a real ground, it's a virtual ground, right? So that means what we can do is that, well, we're going to set this voltage to be 0 here, okay? Therefore, right, the voltage drop from V in to V in minus, right, that's just going to be whatever IR is. So we're going to use Kirchhoff's voltage law. Okay, so V in minus whatever the current is, R1, is going to be equal to 0, because that's the virtual ground we got here. Okay, all right, so that's nice. Okay, well, but we want something to relate to V out. Okay, V out, in order to get to V out, you can also keep going on this, right? Go from 0 over R1, sorry, R2, right? Okay, so that's going to be minus I, it's the same I, interesting, right? R2, right? Oops, sorry about that. Don't have that equal sign there. Minus R2 gives you V out, whatever that is, right? Because you started at 0. Okay, right? So you start at 0, you have a voltage drop. Let's divide that up. Start at 0, you have a voltage drop, then you get to V out. Okay. Well, since these currents are the same, we can solve one or the other. So let's solve this left-hand one. So I is actually Vn over R1. Substitute back into here, right? Once you get minus Vn over R1 times R2 equals to V out. And therefore, V out is actually equal to minus R2 over R1 times whatever Vn is. Nice, right? So therefore, the gain is minus R2 over R1, right? So whatever the ratio between those resistors are, that gives you the application of the circuit with a minus sign. That's why it's called inverting amplifier. Okay. So that's how you analyze this type of circuit. You just, apply the 2 golden rules as you need to. Okay. And then you just do Kirchhoff's loop law. You can do Kirchhoff's voltage law, and you can do Ohm's law, right? Or the super Ohm's law, because you can connect like capacitors and inductor to this also, not just resistors. Okay. All right. So we have this gain, and it's actually interesting that, well, the book actually goes on to do the a different analysis, but what I want to talk about is actually the stability of this circuit. What I mean by stability, so if your input is just, instead of getting exactly, 1 millivolt, if it's off by 1 millivolt plus, a tiny amount, let's say a microvolt, right? Would this amplifier amplify that signal, that noise, and make it much bigger, or so therefore making it worse? Or it will amplify things in a way it'll be opposite of it, so therefore, right, it reduces that noise, okay, on your output. And we can see how that works in this case. Okay, so another way to analyze this, which is what the book tells you, is just think about this in terms of a voltage divider instead of doing all these derivations with Kirchhoff's voltage law. Okay, because you can think about this. I'm going to go up here and look at the circuit once again. Right. Okay, you can think about this as Vn. Right, there's the R1, and then you have Vn minus here, right, and then you have R2 here, right, and then you get to V out. Okay, right. This is familiar because we have something that's similar to this already, right? So it's R1. We take this as V out, right, and this is ground usually. This is our typical voltage divider circuit. Well, it's very similar, except that, the 2 of those points are actually labeled different, right? So if you analyze this using the voltage divider equation, what you end up with, okay, is that Vn minus this middle point here, okay, is actually going to be the voltage divider equation of Vn plus some other part, plus the second set of voltage divider equation, which is instead of R2 being on top, you have R1 being on top, because you're basically shifting this Vn minus point. Instead of starting from 0, you're shifting it out by V out times R1 plus R1 over R2. Okay, so because that goes with this circuit. Okay, I didn't want to try to confuse anyone. Okay, but this is an alternative way to do this analysis. Maybe I'll put that in the pre-lab just so we can play around with that. Okay, but the result is the same. Basically, V out is going to be the ratio between R2 and R1 with a negative sign times Vn. Okay, so what we're going to think about is that, okay, what if we don't get exactly that output, right? Let's say there's a little bit of noise and the output actually gets a little bump, and we're going to call that bump epsilon here. Okay, tiny deviation. right, from the ideal output. From ideal. Okay. Okay. Let's see what happens. Okay. So if we plug that back into this previous equation up here, what we're going to end up with is that all the V outs and V ins kind of subtract each other out, and you end up with just this term epsilon that's proportional to epsilon times R1 over R1 plus R2. Okay, so what happened is that this error, right, that's at your negative input, right, will create a difference in V out by being amplified by this number A, which is the open loop gain. Okay, this open loop gain will have a little negative sign in front of it because it's a inverting amplifier, right? Because the feedback loop is always connected to the negative input. Okay, this is actually going to be opposite, right, of this deviation. Okay, it's going to create a little small error that's going to be, you know, if we just use the sign, if we just take epsilon as positive, right, because epsilon could be positive or negative, let's just, we take it for positive, right, that means the input side is going to be off by some positive times, you know, R1 over R1 plus R2, but then the output will have the opposite effect, right, because it's this negative sign in front of it. Okay, right, so opposite voltage will be fed back to the input, and what that does is that it basically corrects that error. Okay, in fact, a lot of time it actually overcorrects it, and you're going to see this, and we'll try to get you guys to see this in the lab when a amplifier actually overcorrects. Okay, but right, by correcting if you have something that's too positive and then you subtract from it, right, it corrects for that. Well, now the number is too negative. Well, we're going to have the opposite. We're going to add to that. So it kind of oscillates until it gets to the right number. Okay. And this circuit design is known as the negative feedback. Okay. Once again, I'm going to do the analogy that I learned from, it's 2005, from 20 years ago. Okay. So the analogy that was taught to me is that, well, if you think of if you're driving on the highway, right, you have a 2-lane highway, right, in your car, right, headlights this way, right. If you start veering off to the right, right, let's say you start seeing, oh, my car is drifting to the right, the direction you want to turn your car is to the left, right, right. Hopefully that makes sense. Veer right. Right. The way you correct for that is to turn your steering wheel slightly left, right, and that'll bring you back to the center, right. But sometimes maybe you overturn too much, right, and now next step is that your car is veering to the left instead. Well, then you correct a little bit, right, back to the right. Okay, and hopefully by, you know, a few iterations of this, you're actually going in a straight line. Basically, your brain does this without even thinking about it, because we're being trained to, you know, drive cars and stuff like that for you know, since we're 15. Okay, at least in the US. Okay, so that's the way you think about negative feedback, is that, oh, you see something going to the right, because if you're veering to the right and you start turning to the right, right, you're going to drive off the road, right? So if you start veering to the right, you actually turn the opposite direction, so you have a negative feedback, so that you actually correct for it. Okay, so that's basically how your op-amp with negative feedback works. Okay, and this is running off a inverting amplifier. One thing to notice is that whenever this feedback loop that I noted before, right, if this feedback loop is connected to Vin minus, that's always going to be a negative feedback. There will be some usage where we're connecting to the positive, but we're going to see that probably next module, not this one, when we talk about comparators. All right, let's see. Let's keep going. How much time I did? Okay, let's do one more circuit. Okay, and this is the summing inverting amplifier. Okay, I'm going to skip the non-inverting amplifier and just have you guys do that in class. Okay. So this is a really useful circuit because passive circuit, meaning passives, meaning resistor, capacitor, inductors, right? All those components that doesn't need a power supply, right? Or even a diode, right? It's really difficult for you to add voltages together. The reason for that is that when you have a resistor chain like this, if I just want V1 plus V2, right? You put it on two resistors, right? And you think, oh, the output here should be proportional to V1 plus V2, but it's not, because what's happening is that, if V2 is bigger than V1, the current starts going into V1 instead, right? Not directly to where you want it. So that's going to be a problem, but right, op-amp fixes this, because remember, one of the golden rules of op-amp is that the input does not draw any current. Okay. And this basically forces, and then golden rule number 2, right, forces this to be your virtual ground, right? So I'm going to put 0 volts here, right? So therefore, whatever current comes out here will not go into the other side, unless some of these are negative, right, which you don't want anymore. Okay, so that's sort of interesting. Okay, so that each input is forced to go into V minus, which is, by tying V plus to ground, which is golden rule number 2, right? It forces this to be your virtual ground. Okay, so the current, right, you got I1, I2, I3 here, and then so on, right? Each of the current is going to be proportional to the Vn divided by R1 on R2, R3, the input resistors, right? And that's going to get amplified by RF. Okay, so all the current here gets combined here, but it's basically this I here, right? I'm going to call it IF actually. It's going to be I1 plus I2 plus I3. Okay, and since you're adding these currents together, that gives you a amplification by RF over each of the resistors. Okay, and that'll give you basically a way to add different voltages together. Okay, so that's sort of a neat thing. Okay, and then in this case, since you're not concerned with amplification, your RF might be on the order of R1, R2, R3, right? Because then you get unity amplification. Okay, of course you cannot do that with different R, but maybe pick R2, the middle number, to be that. Okay. All right, so that's the example I'm going to go through. Next, we're going to talk about combining what we learned here about operation amplifiers with some active filtering circuit that we're going to see and built in the lab.